So, welcome again, everyone, in the 10th session of this GAN program. And in this session, we have a lecture by Professor Arni S.R. Srinivasa Rao. And this lecture is based on dynamic risk prediction or cardiovascular diseases and statistical model for the diseases. So, as you all already know about Professor Arni S.R. Srinivasa Rao, that he is working in Medical College of Georgia, Augusta University, Georgia, USA. So, on behalf of all the organizing team members and participants, also, sir, I would like to welcome you on the platform. And now, platform is all yours. Over to you, sir.
Yeah, thank you. Thank you. Uh, all the participants, a very good evening. As we stopped yesterday lecture at the theoretical understanding of the classification of states, we discussed the gambler's ruin problem and the model, which is also similar to a random walk model. So random gambler's ruin model also a random walk model. And then we started, we wanted to introduce a new phase of our course that's on classification of the states and how can we classify states into, I mean, within a state space, how we can classify the states into various categories. Let us see that now. Let me start the course contents. So as always, feel free to stop me. So today's lecture will be a little bit theoretical, and also a lot of intuition is needed. And as always, carefully, I hope you carefully follow it and then stop me if anything is not clear. But this is essential part of the stochastic processes, and also we'll see some examples, numerical examples during this lecture. And then with this, with content, you would actually reach a lot of advancements in your understanding of the stochastic process with this today's lecture. So let me start my slides.
Hello.
Classification of the states. Why do we need to classify? Because each state, depending on the transition matrix, the classification changes. And this classification is very essential to group together. We need to group the states according to the properties they have. So as I mentioned in the introduction right now, so let us see how we can classify. For any state I, we define two random variables. Now you focus here, as I mentioned in the beginning, two random variables, Ti and Ni. Just notation only, but the meaning of Ti and Ni as follows. Pi, by the way, I forgot to mention, I hope you all yesterday revised the notes on Chapman-Kolmogorov equations and the derivations. And if anything is not clear, sorry, I should have told in the beginning, if anything is not clear, feel free to ask me that also. Those questions on that also, end of this lecture. Not a problem. So let me start with two random variables, Ti and Ni. Ti equal to minimum of n. What is our n here? Again the same, n is a time, xn. This n stands for the time step. Minimum of n greater than or equal to 1, and xn equal to I. So if you have, if you're writing on tablet, or if you're writing having pen and paper, write down and see what exactly as you write, you see, observe that minimum of n, that means minimum of the time step, minimum of n, and xn equal to I, n greater than or equal to 1. So minimum of n such that this n is 1 or more than 1, and x of n equal to I. Xn equal to I means what? At the nth time step, the random variable is at state I. State I, again, quick recap, if the head and tail is the state space, xn stands for suppose I is equal to h, at the nth time step, xn takes the value h. This is the time step, xn takes the value h. But minimum of such n's, that means Ti stands for first time. Minimum of n means all this n. It could be x1 equal to heads, x2 equal to head, or maybe x3 equal to head. But then minimum means first time. First time, all the minimum of that, hey, x2 equal to h, x3 equal to h means this n is equal to 2, because first time it has reached head in the second time step. That's what Ti equal to minimum of n greater than or equal to 1, xn equal to h. And the second random variable, we define ni equal to number of such times. Number, this hash means number. Number of n such that n greater than or equal to 1 and xn equal to I. So these two are also random because we don't know in advance. Xn equal to I, and number of times that particular state has, the random variable has reached that state. The first thing is the first time reaching, and this is the number of times reaching. These two random variables we defined. As I explained, the Ti represents the time step and Ni represents number of visits or number of times reached the state I. If there are no n that defines that, never it reaches, there is a particular state. Suppose you toss a coin, you keep on tossing a coin, you may never get head in first 10 times, and you stop your experiment. After 10 trials, you never obtained the head. So we write in that case, Ti tends to infinity or Ti equal to infinity. No n that satisfies the definition of Ti. We write, that's a notationally Ti equal to infinity we write. As I mentioned, this is theoretically, this is important. The intuition what we are developing in this lecture is very important for having a more deeper understanding of the stochastic processes. If there are infinitely many n, we write ni equal to infinity. This number in so many, infinitely many keep on reaching that, visiting that state or reaching the state I, we write ni equal to infinity. So Ti equal to infinity means never, no minimum value, never reaching that state. Ni equal to infinity means reaching several times. So Ti less than infinity means Ti is finite. And Ni greater than 1 both are same. Because Ti less than infinity means ith state the state I has been reached by the random variable. That means Ni is 1 or more than 1. Number of times reached. So Ti is finite means Ni is greater than or equal to 1. Both are same. So based on that, we define two more functions. As I discussed, the theory is very, very important. And we need then application. You need to apply. Then only once you understand theory, you could able to bring some novelty within the theory yourself, and then apply to data according to the situation. If you don't know theory, we need to apply only whatever little bit knowledge you have. But if you have theoretically, you have idea, you can apply according to the data availability, because always the data may not be available according to our own situations, our own knowledge. So if you have a solid understanding of what's going on, you can actually build your own new theories. So for I comma j belongs to state space S. So maybe before I go to that, let me give some examples of the previous two definitions. Let me add a slide here. So we define Ti. Suppose the sample space S equal to H comma T. And then you have, say, x0 equal to T, and you only tossed a coin 3 times. Suppose that's an experiment. 3 times you toss a coin. Well, this don't get confused with this T with the T notation there. This T stands for the tail, head and tail, that thing, and that TI is a notation for the first time reaching. For the sake of this thing, let me. And x1 equal to head, and x2 okay, your experiment is done. You toss 3 times. Now, according to our definition, Ti, the random variable Ti equal to what? Minimum of n such that n greater than or equal to 1 and xn equal to I. So T, because these notation, these concepts are important for classification. Now T of I means I is a state. So pick any state, let T of H heads equal to minimum of n. So minimum of n such that n greater than 1 and xn equal to I. So xn equal to I and the minimum of that. So xn equal to I, when that happened, x1 equal to heads, the T of head, x1 equal to head, x2 equal to head. So minimum of 1 comma 2 is 1. So T of heads is 1. N of heads, number of n of head, number of n such that n greater than or equal to 1 and xn equal to I. That's a definition. This means n of heads means number of times in that experiment had occurred. That is equal to 2. So T head is 1 and head is 2. Similarly, T of head, a T of tail. T of tail is, okay, here's some adjustment in the notation. Let me change that to 1, 2, 3 instead of 0, 1, 2. Because I start from n. Anything is fine, just notation only. 1, 2, 3. And then these would be 2 comma 3. So T head is 2. Yeah, N head would not change. So T head is 2. So as I'm working on the screen, you also please work along with me. So T tail, let us understand again T tail. T of tail is again minimum of N. So first minimum of N, tail occurred only once. So T tail equal to 1. And N tail also 1, only once it occurred. T-tail occurred at 1, and that's a minimum. So these are just these two are examples how to compute the T and N. So let us understand two functions based on the T and N. As I mentioned, these after the Chapman-Kolmogorov, these two play a very, very important role in understanding this advanced stochastic process. You can, once the foundations are clear, one can build their own further theory. So then the new again notation Fij, we define Fij within the bracket superscript n is defined as probability Tj equal to n given x0 equal to I. Probability Tj equal to n, Tj, that means this suffix is your state here. Tj, the minimum time, minimum number of first time occurrence of first time, reaching the random variable xn, reaching the state j first time in the nth time step. Tj equal to n means reaching the state j for the first time in the nth step. That's the meaning of that. You write down as I speak the meaning. Probability that the random variable xn reaching the state j in the nth step. Given that x0 equal to I. x0 equal to I means it begin from the initial state, initial time step, it was in the state I. So it begin from state I, reach j at the nth step for the first time. First time reaching j at the nth step. That means first time reaching j. So again come back to our Markov chain notation there. Starting from I, and then reaching state j only at the step n, at the time step n, not before that, because first time Tj means what? Minimum time it took to reach is n, that means first time reaching. So first time reaching n means before n, 1 less than or equal to L less than n, before the time step n, it has not reached j. That means XL for this L not equal to j for all the values of L less than n. All the values of less than n and reaching j. As I mentioned, these are very, very important. Just notation only, but intuitionally, all have to think as I am teaching. All have to think thoroughly as I am teaching. Not understand, not a problem, but you have to ask and clarify the things here very clearly. But this course is for you. This is very, very important. Not only building the stochastic models, we need to understand, we have to classify the states in a stochastic model. So Fijn equal to Pi, probability xn equal to j, for the Tj equal to n, or these two are same. Tj equal to n, first time reaching, starting from I, reaching first time j in nth time step. That's the minimum time to reach j is n time steps. And then that means this is prior to n, it has not reached j. So that means Fij n equal to 1 to infinity here. That means if n equal to 1, this n equal to 1 means reaching j for the first time. N equal to 2 means reaching j in the second step. N equal to j 3 means reaching j in the third time step. That means if you add up all the probability, reaching for the first time, reaching for the second time, third time, and so on, sum of all the probabilities. So probability Tj is finite, reaching some time step, n equal to 1 to infinity, x0 equal to I. That with the summation we denote by the symbol Fij. Fij n, this indicates is reaching for the first time j in the nth time step. Fij means sum of all such possibilities. So Pij is always Pij is our notation for probability of transition from I to J. We learned in last few lectures. Fij means reaching for the first time. Pijn means here I to J in n time steps. We didn't say for the first time. This need not be first time. I to J might have occurred, might have reached for the some other step, maybe prior to n. But Fijn means reaching for the first time. That's why probability of I to j in n time steps is greater than Fijn or equal to Fijn. Because first time reaching. So this probability is higher or equal to Fijn. Just automatically you would, once you intuitionally see, that will be correct. Let us see another example. Suppose an ordinary 6-faced die thrown 10 times and outcomes are recorded as follows. Suppose x1 equal to 6, x2 equal to 4. The 10 times you draw, you just you throw a die. These are the outcomes. Then F639 example, F639 means starting from 6, reaching 3, 9 in the first time reaching the state 3 in the 9th time step. So T3, that means T of 3 is 10. See here, T3, reaching state 3. State 3 never occurs. This is 6, 4, 2. These are the states. This is the time. So state 6, 4, 2, 5, 1, 2, 6, 1, 3. So reaching the state 3 only occurred first time in the time step 10. That is T3 equal to 10, x1 equal to 6. Beginning from 6, reaching the state in the reaching the state 3, this is the state in the 10th time step, that is a 10. So F63 is here, n equal to 1 to infinity, n equal to 1 to 9, F63. All the time steps reaching. So F63 is sum of only one, n equal to, the number of times reached 6 to 3. So F631, F632, F639. So all are 0, 0, 0, reaching the F63 in the 9th time step. Because they are all 0. F63, did it reach in first time step? No. Did it reach in the second time step? No. 6 to 3. Did it reach in the 8th time step? No. Did it reach 9th time step first time? Yes. So this is the only probability. So F63 equal to F639. So as I mentioned please focus, and this is how we are computing all these things. So this again the same thing I explained here in another slide. So now the 11th time, same experiment, we toss a die, again we throw the die for the 11th time and record the outcome, and 11th time suppose x33 equal to 3. But still T3 is 10 because first time reaching is T. So T3 is 10. T3 is 10. So that's why P639 is greater than F639. We have probability P63, probability 6 to 3, 6, and then reaching 3 in the 9th time step is greater than F639. We have F63 first time reaching in the 9th time step. So that's why this example, I'm going to send you the slides. But you have to carefully follow during the lecture also, all of you, because this is for you all, and this is important. This will actually take you to the understanding of the classification of states. So we are already reaching the advanced stage of the stochastic process. Now, based on the definition examples, we say a state I is recurrent state if Fii equal to 1. Fii equal to 1 means what? F starting from state I, reaching the state I, same state. You begin from the state I, reaching the same I, the chance of that is 1. So I to I can come back in the one time step, 2 time steps, 3 time steps, or infinitely many time steps, but it will come back for sure. Starting from the state I, returning to the same state is sure. That is equal. That means it is a probability of reaching that is exactly 1. That means sure to come back. Then that state is called a recurrent state. If it is not 1, else means if the FII is not 1, that means it's a transient. That's how. Anyone asking question?
Yeah, sir. I have one confusion, sir.
Yes, please.
Sir, you said that Fijn is the probability that random variable reaches state J at nth the first time. So
yeah, first time.
Does it mean F6 the superscript 9 up to 9th step xn is not 3? I have some confusion about this superscript 9.
Yes, 1 to 10 means 10 minus 1 is 9, you see. Yeah. Starting from 1.
Yes, sir. Starting from 1. So, 9th step पर तो sir 3 नहीं आया. X10 is 10th step na?
No, 10 means, the starting from 1, it took, starting from 1, it's not a 1, it's a beginning. It's a beginning step. Beginning means your first time. It started 3, 1, so you... First step. This is the first, after 6, leaving 6, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
Good question. Yeah, that's a good to clarify that. So leaving the state, you left the state here and reaching back in the 9th step.
X1 is initial step, na? 1 is initial step. So initial. 1 to 2 is first step.
First step.
Okay, sir.
So FII equal to 1 means the state is recurrent. FII equal to 1 means it could reach I to I, starting from I, reaching I, it could reach in the first step. Minimum. FII is what? How we define FII? Sorry. FII we defined as, this is I, instead of J you replace by I. FII is summation n equal to 1 to infinity FII n. N could be 1, n could be 2, n could be 3, whatever infinity. So reaching FII is 1 means, the summation 1 means reaching is sure, assured. It cannot escape. It has to come back. Starting from that state, it will come back. So leaving the state I, if it is a probability to come back to the state I is equal to 1, it may take infinitely many steps or it may take finite steps. Doesn't matter. But the surety, it is assured that it will come back to the state I, then the state is called recurrent. If the probability to come back to that state is not assured, then it is called a transient state. Recurrent and transient, 2 states are, so in the stochastic process, the states are classified recurrent state or transient state. So that means, this is what I explained. FII equal to 1 means I to I, all these things. I to I, n coming back. So that's why once the random variable leaves the initial state I, it has certain probability to come back to the state I after n steps. For n equal to 1, thus the state is recurrent if the chain starting from state I is sure to return to state I at some future time. So it doesn't happen. So FII is less than 1 means what? Else means FII is anyway more than 1 is not possible. Probability would not cross 1. FII else means FII less than 1 or not equal to 1 is same as not equal to 1 means it cannot anyway exceed 1 So FII not equal to 1 or FII less than 1, same meaning. FII less than 1, it is called a transient state. Less than 1 means once the random variable leaves the state I, the chance of coming back to state I is not 1, no guarantee. Then that state is called transient state. So for a transient state, the finite probability never returning to state I. There is a finite probability that it will never come back. So in the random, now coming back to the random, you all remember that, random walk example or a gambler's ruin example. So instead of that, let me add a new slide. Oops. See, this is a random walk things we discussed. Or let us take a gambler's model. So gambler $0 come back home or $N come back home, and the gambler goes to the gambling center at say 5 rupees in his pocket. That's where he enters each time the gambler plays a game, it will become either $6 or 4 rupees. No other option, isn't it? Each time a gambler plays a game, either come back to 4 rupees or 6 rupees. Become 1 rupee, suppose for each game, winning or losing. Now, starting from 5 rupees, a gambler may win may win a game, again another game, again come back to 5 rupees, again go to 6 rupees, again 7, again 8, again 99, again 98, 97, and so on, again 5 rupees. Isn't it? But there is no guarantee that the gambler once leaves 5, it will come back. Even after 99 rupees, after at that stage 99, gambler wins one more game, reached 100, n equal to 100. Suppose you want to fix n equal to 100. At 99, gambler wins one more game, game over. Gambler leaves gambling center. Similarly, gambler loses all the money, gambler leaves so 0 and n are known as absorbing states. Now in this case, are we sure that a gambler with 5 rupees in the pocket will come back to 5 rupees at some stage? Or the gambler at state, these are all states. 0, 1, 2, 3 are the states. Each rupee is a state. Are we sure that a gambler leaves the state 6, is come back to state 6? No. We are not sure. So, intuitionally, you all agree that these are all the states excepting 0 and n, they're all recurrent states.
Transient.
Transient. So, there are transient states. No chance of returning back.
No, maybe return back, but there is no surety.
No surety. That means probability is not 1. So in the gambler goes to the center, so your x0 is, you can assume as 5 starting. Now x1 it could be, x1 is either 4 or 6. So first time reaching, that means your T4 is 1 if it reaches 4, or T6 is 1. first time reaching. The T6 means here this is a state. This is a state. And this is the time step. Time step, this is a state. So T6 means this is a state. Reaching the state 6 for the first time. We're starting with 5 rupees. First time reached only, there's a possibility to reach only in the first time step. If the gambler reaches 4 in the first time, I mean the gambler loses as soon as enter the gambling center, loses the game, he'll go to the 4. So first time he cannot reach 6. First time he reach 4. Suppose he reaches first time, he wins the game. T6 is first time, T6 is 1. Minimum time it took to reach, only 1. But as the game progresses, there is no guarantee that the gambler would come back to 6 because it's random. So we'll also see examples as we progress for the recurrent. So all the states here are recurrent, and 0 and n are known as absorbing states. Absorbing, game is over. Absorbing. So 0 is absorbing. This is 0. Similarly, n. Yeah, that's what it means here. Every absorbing state is recurrent. That means this absorbing state is recurrent. That means that's what I explained here. So these states starting from 0, I mean once the 0 state is 0, remain 0. Once the gambler reaches state n, remain there. The game is over, so they remain in the n equal to 100. So that's why absorbing states are recurrent states. So this result is, that's a homework you all can.
Please clarify it again why these two states are recurring, because it is not also sure that the gambler will reach rupees 100.
Yes, because the gambling, according to our the game Gambler's Ruin model, gambler will quit the game, either reaches size the gambling the rupees 100 rupees, I mean the n, some size n, or gambler quits when the gambler has a 0 rupees. That's the Gambler's Ruin model. Gambler will go with some rupees in the pocket, and with all the money is over, he'll come back. That's a $0, 0 rupees. Or if we reach some size n equal to 100 rupees, that's the rule of the gambler rule. That's how say gamblers gambling centers are defined. Certain rupees gambler reaches, he has to quit the game, quit the gambling center and come back.
The gambler cannot quit with rupees either more than 0 or less than 100.
Correct. Gambler have to play. That's how, I mean, these are probabilistic theoretical so that's how the definition of the Gambler's Ruin model. Just for the sake of realistically, this is the rule in the gambling centers. I don't know. I mean, because no one fixes such rules. This is theoretically to demonstrate the recurrent state and transient states. Gambler's Ruin models are defined.
Okay.
So Gambler's Ruin model, as we say other day, as we defined yesterday, I think, a gambler quits the gambling center either at 0 and n. In between, he cannot quit. He or she cannot quit.
Okay, sir.
So that the two states, then that's a recurrent and transient. So make sure that all of you understand that. Now using the recurrent transient, we define whether that each state communicate to each other. Let us understand what do we mean by communication. Then because again I will touch base on the transition matrix. What we learned transition matrix, again that will bring it here. And then we define the communication of the classes, whether two states communicate to each other or not. The two states I and j are said to be communicate to each other if Pijn is greater than 0. Pijn means what? Reaching I to j in n time steps, need not be first time. Pij need not be first time. Fij stands for the first time. The notation small change. Pij need not be first time. I to j in n time steps. Pij, I to j nth time step and greater than 0, and Pjim greater than 0 for some positive integers n comma n. But the I and j we denote by I and j. When you write double arrow, that means I and j communicate to each other. So Pi to j, some probability to reach I to j. There is some probability to reach I to j and some probability to reach j to I. In some time steps, need not m and n could be same or different. For some positivity, I to j in n time steps, j to I in m time steps, the positive probability to transit from one state to other state, we say I and j communicate to each other. Two states communicating to each other means probability to transition between these two states. The transition matrix we formulate other day. That means transition matrix also we saw, the transition P00, other things. So that is each state communicate to other state. If each state I communicates with itself, then we write I to I. That's what it means. So if I to j and j to k, j and k, I and j are communicating to each other with double arrow, j to k communicating each other, then we say, then you say I and k also communicate. If I is communicating with j is communicating with k, then I is communicating with k. Associative law. And then we define closed set. So this is I hope you know that you all understand that. Then we define, any question?
No, sir, I think it's transitive law, no?
Sorry? No, transient recurrent ho gaya. Transient means?
Transitive. Associative law you are telling.
Yeah, I to j to I associative, and then I to k, that happened, you see, that's a transitive.
Yes, sir.
I and j associated, j and k associated, I and k transitive. These two, I and j are communicating each other. That means j and I to j, j to I. Similarly, j to k, k to j. So I to k is. So these two associate, and then that's why this is transitive.
Yes.
So once that is there, sorry. Any question?
No, sir.
Thank you. Yeah, closed set. So these are all important too. Again, why we doing all these things? The motivation is that the transition matrix which we formulated in the Markov chain, the transition matrix we want to break down into pieces, because the larger the matrix, the more complicated it is for understanding. Even for COVID, when you formulate that, so larger the transition matrix, we need to break down into pieces, smaller pieces, smaller sets of states, such that we can handle them. We want to reduce the bigger transitions matrices. That's the reason we are learning that. So S be the state space, and suppose let's be a state space, and suppose C subset of S. You take a small any subset which is proper subset of S. Then the C is called closed. If Pij equal to 0, Pij equal to 0, that means I to j, the transition probability I to j starting from state I reaching j is 0. For I belongs to the closed set, the set C, and j does not belongs to C. Example, let me write out here only. That means, what do we mean by that? Suppose S equal to 1, 2, 3, Now C, take it as a, say, set of any number, say 2, 4, 6. Now, the set C is called closed. This is called closed. Pi is 0 for I belongs to C. I belongs to pick any number, any state. Say, let us pick 4. 4 belongs to C. So P, 4, 6. 6 also, say 6 is in the C. Let us take some state which is not in the C. Say P4, 5. P4, 5. So 4 is in the C, 5 is in the S. That means
this will be 0.
Any question? Okay. So 4 belongs to C, 5 does not belong to C. So P4, 5. If P4, 5 is 0, probability to reach P4, 5, 0 and P2, 5 or 2 to some other state outside C is 0, 4, 6 to outside C is 0. Then we say C is closed. That means no transitions are occurring outside C from any state C. Then we say C is closed. But in general, all of you know the closed set, open set there.
Sir, excuse me, sir.
Yeah, please go ahead.
P4, 5, 0, P4, 1 is also 0, P4, 2 is P4.
Yes. For
3
each
is also
state,
0.
Yes. For each state, no transition should occur from a state in C to the outside C. Correct. For each state I. That means here you see that here. That's why you write this meaning of that is for all J belongs to C, Pij. J belongs to C, Pij equal to 1 means the communication should happen only within the C. Communication should happen only within the C. Then we say it is closed. But in general, we define closed set in the real analysis. If a set is not open, we say it's a closed. So if in general, the open set, if you take some space, metric space, X metric space, then if you pick a point here, any point, you should be able to draw a ball around that point, and the ball, at least one ball should be completely inside the space. This is A. Suppose A belongs to X, X is a metric space. Or an interval, let us say, instead of, we can define for a metric space also. Or let us start with A. So if A belongs to X, this is a point A, and B ball with the point A with radius R for R greater than 0. This ball B, A, R, this should be subset of X. For at least, not all the radiuses, at least, is it at least 1 R? If you draw one ball, if it is one ball completely subset of X, completely inside the space X, then we say if A is arbitrary, if that is true for any arbitrary point inside the space X, if it is true, we say that X is a open set, and the set which is not open we defined as closed. That's why you take the, say it's a 3, 4. 3, 4 on the real line. If you pick a real line on the 3, 4 interval. So you can, if you take a point here, say 3.8 something, you can draw a ball or interval. Then that interval is completely in the set 3, 4. But if you take a point on the 4 itself, 4 itself, 3 comma 4. So the point 4, if you draw a ball around 4 or interval around 4, 4 minus epsilon to 4 plus epsilon, you see that this interval 4 minus epsilon to 4 plus epsilon for epsilon greater than 0, this interval is not completely inside the interval 3 comma 4. So 3 comma 4 is not a open set. That's why 3 comma 4 anyway a closed interval. So it's not a, but if you take an interval 3 comma 4 open, this is open. Any point in this interval, you take it any point, you could be able to draw a ball, or interval, a ball in a 2-dimensional space. Disk, you can, or a ball in a metric space. If you draw an interval, the same concept, more or less the similar concept applied here. So you cannot take 4 anyway, because 4 is not part of your interval. 4 is, you cannot pick a point in the set. So if S is a set, 3 comma 4, open interval 3 comma 4, you pick any point your choice between 3 and 4, you can draw an interval, you can choose an interval with an epsilon with a neighborhood. That 3 comma 4, that the point neighborhood of that point will be completely in the set. So that means that interval, any point, you can choose a point as much closer to 4 as possible, as much closer to 3 as possible. In any point in between, you can happily draw an interval that completely inside at least one interval or one ball or one disk, whatever disk, one interval which is completely in the set. That's why 3 comma 4 is an open set. A set which is not open is called closed. Similarly, here we define any from transition from C closed set to the, if you cannot make a transition, if you cannot make, these two should not be communicating. So communication between 2, 3, 4, 6 should be within that set. Then it's called C is closed in terms of the stochastic process, the states. The C is a subset of the state space S. So subspace, kind of a substate space. So same thing, the I to J, for J equal to C, that means you cannot reach outside. That means probability of reaching a set within that should be equal to 1 from anywhere to anywhere. So these are essentials for. So let us take this kind of some arbitrarily designed matrix. Suppose this is a transition matrix. Let us understand that. Here you see that this is the matrix given to us. P11 is half, P12 is half, rest all are zeros. See here P21. So if you, yesterday also I showed how to draw a 1, 2, 3, 4. These are the states. 5, 6. Okay. States. So 1 and 1 are communicating. So there is a probability to communicate with itself. Let me change the color. They are communicating with itself, 1 with a probability half. And 1 to 2 transition is happening. 2 to 3 is happening. Yes, 2 to 3 is probability 1. And 3 to 1 3 to 1, 3 to 4, 3 to 4, 3 to 5. And then 4 to 4, 4 to 4 communication happening, 4 to 5, and 5 to 6, and 5 to 6 and what? Then 6 to 5. Okay. Now carefully observe here. Random variable leaving X, can it come back to leaving random variable leaving 1, state 1, can it come back to 1? Just carefully see.
Yes.
It can 1 to 2, 2 to 3, 3 to 1. It can come back. Leaving 2, can it come back to 2?
Yes, sir.
Yes. Leaving 3, can it come back to 3?
Yes.
Leaving 3, can it come back to 3?
Yes, sir.
If it only goes to 1,
Yes.
but if it goes to 4,
No.
we are not sure,
Yes.
isn't it?
Yes, sir.
It is not always sure. Similarly, 1 to 2, 2 to 3, 3 to 4 reaches, there is no way to come back to 3. Isn't it?
Yes, sir.
Similarly for 2. But 5 and 6, if you see that 4 once leaves 4, there is no mechanism to come back 4. But if a random error leaves 5, it can go where? Only to 6. And if random error leaves 6, where it can go? Only to 5. 5 and 6. So 5 and 6 are recurrent states. So leaving 5 infinitely many times, the random variable can come back. Okay?
Yes, sir.
Similarly, leaving any other state, it can come back, but we are not sure. Leaving 1, it can go to 2, 3, but some chance of coming back, but infinitely many times it may not come back. That's the catch point here, understand? All of you, that's the distinction between a transient state and a recurrent state. So
Yes,
6,
sir.
that's why this 4, leaving 4 only 4 to 5. You see the 4 to 5, 4 to 4 or 4 to 5. But once the random variable at 4, the chance of staying there probability half. Once leaves 4 to 5, the chance of going to 5 is for half. But 5 again, it can go to 6 only. 5 to 6 probability is 1. So always, as soon as reaches 5, random variable reaching 6 is 1. For sure it reaches 1. You see, that means probability to reach 5 to, that means it won't stay at 5 at all. See, it's not probability to stay at 5 is 0. That a random variable doesn't stay at 5, reaches 6. As soon as reaches 5, reaches 6. As soon as 6, reaches 5. So 5 to 6 oscillations keep on happening. So 5 and 6 are recurrent states. So that's the idea of the recurrent, transient, and of course, because it's a crash course, you need to make your own several examples. I hope you construct yourself. This kind of, so this is a distinction between so 1, 2, 3, 4. There is a probability to come back to 1, but it is not. That means that in this case, F11, not P, F11 less than 1, F22 is less than 1, F33 is less than 1, and so on. Whereas F55 is equal to 1, F66 is equal to 1. So I would like to stop here for a break, and then would be happy to answer any questions in this lecture or a previous lecture on the Chapman-Kolmogorov, and then we'll proceed after the break. And again, tomorrow would be more. We'll have the. Let me see. After today's lecture, this thing, we'll have. Again, we'll come back to some applications, real world applications. In public health, and yeah. So feel free to stop me if it is anything not clear. These are all essential essential material for you to stand on your own for advanced stochastic process.
Am I audible?
Yes, yes, please.
Okay. Thank you so much, sir. So now we can take a break of 10 minutes.
Yes, if there are no questions,
Yeah.
we can take a break.
Participants, if you want to ask anything, then you can ask.
Yeah, feel free to ask any questions, any of you. As I mentioned, these are all courses for you to understand the advanced theory and then apply it. Applications also will learn. And hope you all received the read sometime between to understand the yesterday's lecture notes and also the mathematical modeling articles. And still, I need to send. I could not locate that the soft copy of the infertility article. One participant asked, I'm going to send that to Professor Kumar today. I'll look at it. I could not get time to yesterday to look at the location where I stored that article. But all the HIV related stuff, whatever models, all that I sent to yesterday, hope you all had chance to look at them.
Of 10 minutes, and after 10 minutes, we will resume back here.
Sure. Okay. Thank you.